Let's talk about the Chinese remainder theorem. So here's the statement again. You have a commutative ring R with identity. You have ideals M1, M2, Mn in the ring, and you write M for the intersection of these ideals. So the key assumption is that the sum of any two distinct ideals in this collection is the whole ring R. So we say that these ideals are co-maximal when that happens. Then the intersection of the ideals is same as the product of the ideals, and R modulo this intersection, or you could say R modulo this product, is isomorphic to the product of the quotients by the individual ideals. Okay. And we prove this little lemma that if you have two ideals, they're co-maximal, then the product is same as the intersection. And to have some example in mind, in Z, co-maximal just means that this any ideal is principal, so AZ and BZ are co-maximal if and only if A and B are relatively prime. We saw that. Okay. First of all, this is true not just for two ideals, but for a bunch of ideals. If you have a finitely many ideals, and you know that the sum of any two of them is equal to R for all I not equal to J, then the product, which in general is a subset of the intersection, but if you have this assumption, then they are equal. We only proved the n equals 2 case. The general case is some induction, and you have to do a little extra work, and it's in the notes. I'll let you look that up. But at least the n equals 2 case we know. Now, let's try to prove this CRT for n equals 2. The general case is written in the notes. So what I want is I want to show. So I have, what's the setup? I have two ideals, M1 and M2. And I know that they're co-maximal, meaning their sum is R. Then I want to show that R mod M is isomorphic to, R mod M is isomorphic to R mod M1 times R mod M2, the product ring, where M is the intersection or the product. The lemma, at least the part that we proved, says that the intersection is same as the product. So I want to give a map from R mod M to this quotient, and you never give this directly, you always give a map from R. Do I know a map from R to this product? Yes, I do, because I know a natural map from R to R mod M1 and a natural map from R to R mod M2, and I can put them together and get a map from R to this product. Let's write that out. Have the quotient homomorphism what do I want to call this? Pi j maybe? From R to R mod mj for j equals 1, 2. So pi j of an element is A plus mj. That's the natural map. And this is a surjective ring homomorphism. So this induces the homomorphisms pi 1 and pi 2 give a homomorphism, which I will call, what's called in my notes? F, I suppose. Pi 1 comma pi 2 from R to R mod M1 cross R mod M2. And this is basically from the definition of a product. Whenever you have a map from a ring to the individual components of a product, you can put them together and get a homomorphism to the product. So if you give me a, f of a is just pi 1 of a comma pi 2 of a, or f of a is just a plus the coset of a mod m1 and the coset of a mod m2. It's the most obvious thing. And this is a ring homomorphism. So what I need to check is that this is onto and that its kernel is exactly M. And then I apply the first isomorphism theorem. Checking that the kernel is M is very straightforward. So verify. So claim 1, kernel of F is the intersection. What does that mean? So A is in the kernel means A plus M1, A plus M2, which is F of A, is 0, 0. 0 of R mod M1 and 0 of R mod M2. Oops. Zero of R mod M1 and 0 of R mod M2. Well, 0 of R mod M1 is nothing but the coset M1 itself, and the 0 of R mod M2 is the coset of M2 itself. So it's M1 comma M2. And this happens if A1 is in M1, sorry, A. There's no A1. A is in M1 and A is in M2, i.e. A is in the intersection. Which we call M, which is also the product, by the way. So the kernel is the intersection. That's claim 1. And claim 2 now is that this F is onto. And this is there's some content here. This is where you have to think a little bit probably if you're trying to come up with this proof. And this uses the fact that M1 and M2 are comaximal. So again, since M1 plus M2 is R, we can write 1, which is an element of R, as a thing from M1 plus a thing from M2 for some, let's actually call them A and B. No, it's fine. M1, M2, some M1 in M1 and M2 in capital M2. Okay. Now what do I have to do? I have to show that this map F is onto. So you give me two cosets, one from R mod M1 and one from R mod M2. So given, so take C1 plus M1, C2 plus M2. That's a typical element on the right hand side here in R mod M1 cross R mod M2 for some C1, C2 in R, right? So a typical element of R mod M1 cross R mod M2 looks like this, where C1, C2 are some element of R. So let's write it that way. So take C1, C2 R and consider the element C1 plus M1, C2 plus M2 in R mod M1 cross R mod M2. That's what a typical element of this ring looks like. What I need to do is I want to find some A, to find A in R, such that when I apply F to A, I get this guy. And I'll tell you which A to take, and this sort of, it's a construction, and you have to think about it a little bit at this point to find this thing, but I'll just give you the answer without much motivation, I suppose, unfortunately. You take this guy. This is an element of R, all right. Let's calculate what is F A mod M1. It's C1 times M2, but M2 is 1 minus M1 plus C2 times M1. So that's equal to C1 plus something times M1. And M1, remember, is from capital M1. So this thing is a multiple of M1, so this is in M1. So this is in C1 plus M1. So A mod M1 is same as C1 mod M1. Similarly, exactly similarly, you verify that A plus M2 is C2 plus M2. Just take this expression and write M1 as 1 minus M2. Okay, take the expression for A up here and write M1 as 1 minus M2. So it's just the mirror argument of the one that we just did. What does this show? This shows that f of A, which is A plus M1 comma A plus M2, is same as C1 plus M1 C2 plus M2. So f is onto. So what have we got now? We have got ourselves an onto homomorphism R mod M1 cross R mod M2, and the kernel of this homomorphism is exactly M. You have the quotient map to M. The kernel is also M. So you get an isomorphism by first isomorphism theorem. Okay, that's the proof for n equals 2. The general proof is a little more than this. Maybe next time we'll apply this in the case of integers.